Hello everyone. Today we are going to talk about our project for predicting item sale price for Big Mart dataset. In this dataset, we have observed there have been 1559 products which have been observed and collected from 10 different stores from different cities, having key features with respect to item identifiers, which are unique product ID, item weights, which are weight of the product, item fat content, retail price, outlet identifiers, outlet size, and the target variable of item outlet sales. This BigMart dataset consists of 14204 observations, which has been split across in training and testing dataset with 8523 observations and 5681 observations for test dataset. Uh, Further moving, we see there have been multiple unique values associated to each of the attribute, which we have taken from the dataset and listed in this. Fat content, identifier, market price, outlet sales, type, visibility, weight, establishment year, identifier, location type, size, and outlet type. We have further moved to do the data visualization using histogram and correlation plot. We have done the histogram for MRP, visibility, establishment year, outlet sales, and weight. Correlation wise, we have done the plotting for MRP, outlet sales, visibility, weight, and establishment year. And we observed that whichever having a value closer to 1 is more correlated. Moving on with data exploration, we have seen that data has been missing for two of the attributes, item weight and outlet size observation for 2439 and 4016 observations, which we have replaced with mean for item weights and by mode for outlet size observation. We have also seen some typo for category in item fat content where items are listed with LF and low fat in a different way. We have tried to put that all together with one entry of low fat with L capital and F capital. We have also seen some non consumable categories which we have categorized as non-edible. We have created a new column for years of store operations. Um, Moving on to the categorical attributes in the dataset, we have done one hot encoding for all the categorical attributes for fat content, location type, size, outlet type, and identifiers, which actually resulted in this expanded data attributes in the dataset. Moving on, we went into model experiments for getting the baseline and hypertuning. Ritesh.
Thank you, Arijit. We started off with our base model. We defined simple linear regression as base model. We calculated when we trained the model using the training set and applied on testing set, we got RMSE as 1133, which was not very satisfactory. So we thought of experimenting with regularized model. We considered Reggian Lasso. We trained model using Reggian Lasso, and then when we tested on test data set, we got the RMSE was brought down to 1116, which was quite lower than the base model RMSE. But we thought of further hypertuning the parameters of Reggian Lasso. So we considered many different alpha values and tried to hypertune using both the methods, the grid search and the randomized search. What we observed was the RMSE was not uh, different than without hypertuning one. It was only a minimal of difference, 0.01 difference. So we thought we should consider some other models for improving the accuracy of our prediction. We consider the tree-based model. So we trained our model using the decision tree and then calculated the RMSE. What we observed, the RMSE which we observed using the decision tree model was 1103, which is 1103, which was quite better than the regularized linear model, which we have considered earlier. And this was without hypertuning parameters. So we went ahead further and started hypertuning the decision tree parameters. We hypertuned the maximum depth of the tree, the number of estimators, and the jobs. We ran for some iterations. This that brought down the RMSE for decision tree to 1085. Being encouraged with these results, we thought we will experiment more with random forest model. We trained our model with random forest, and then we applied on the testing data set to calculate the RMSE. Without hypertuning, we got an RMSE of 1088, which was quite lower. So we further tuned the hyperparameters for random forest model. We tuned the max depth and the number of parameters, the estimators, and number of jobs. That brought down the RMSE to 1080. We further tuned, but the RMSE was quite sticking around 1080 mark. So we concluded that random forest model with hypertuned parameters is the one which is performing better. Having completed this, we thought we will evaluate our decision tree and decision tree and random forest model. We do some significance testing to evaluate that indeed the difference was significant. When we do the significance testing, we got a p-value as 0.0000, which is much lower than 0.05, considering 95% confidence interval, and a t-score as well was like minus 21.46. So this makes us reject our null hypothesis that there is no difference, and there is no difference between the result of decision tree and the random forest. So we conclude that the random forest indeed performs better than the decision tree model, and the difference is significant when we consider random forest. Arijit?
Thank you, Ritesh. Moving on, we did the kitchen sink implementation from assemble approach, where we have taken multiple models, linear regression, lasso, ridge, decision tree, random forest all together, did the fitting and the predicting. Moving on, we did the simple averaging of the prediction using mean, and we came out to the prediction model of it. All the steps have been compiled and laid out in this Python script, where we have done step-by-step execution of it. I hope you like this video. Thank you.
Thank you.